And our speaker today is Hyunju Kwon, member at the Institute, and she will talk about Hölder continuous globally dissipative solution of the Euler equations.
Yes.
Right?
Yes. Okay, so thank you, Camilo. So today I'm going to talk about a stronger version of Onsager conjecture, which is joint work with Camilo. So let me start with the three-dimensional incompressible Navier-Stokes equations, which describes the motion of fluids. So the equation looks like this. As you see, it contains two unknown functions, u and p, where a vector value function u describes the velocity of the fluid, and a scalar function p is pressure. So the first equation is based on Newton's second laws of motion. In particular, the first two terms describes the acceleration of fluid particle. And there are two types of forces. One is generated by difference between pressure, and the other one is generated by the internal friction of the fluid. So in particular here, the passive parameter nu, called viscosity, measures the friction. The divergence-free condition explains the incompressibility of the fluid, meaning that the density of the fluid remains always constant. Okay, so now if we send the viscosity to 0, the limit equation describes the behavior of ideal fluid. And such equation is called Euler equation. And today I'm going to focus on this equation on the periodic domain. So here T3 denotes the three-dimensional torus. So let me first talk about weak solution. If solution pairs, so a solution pair is a weak solution to the Euler equation if it satisfies the equation in distribution sense. But to make every term well defined, we need the velocity to be in L2 space. In fact, the first equation is enough to hold for divergence-free test function. Then the pressure term will disappear because it will look like this in reformulation. So the equation will be only for u. And once you find a weak solution to the velocity which solves the weak formulation, then pressure can be always recovered through the following elliptic equation. So this equation can be obtained by taking divergence to the first equation. And here I wrote the nonlinear term as a divergence form by using divergence-free condition of the velocity. So one can always solve this equation with mean zero condition, and with such pressure and the velocity, they all solve the equation in distribution sense. Okay. So for these Euler equations, there are many important conserved quantity, but in this talk we're gonna focus on kinetic energy, which is defined as a square integral of the velocity. So to see how this quantity changes in time, let's do some formal computation. So first we just inner product the first equation with the velocity, then we obtain the following. follow. And then by using divergence-free condition, one can write the second term as a divergence form. And then take integral in the whole domain. The second term will disappear because of the periodic boundary condition. Then we obtain the conservation. So of course, this computation still holds in whole domain or even bounded domain as long as we have a boundary condition which make the flux through the boundary vanish. But for the simplicity, in this talk, we'll just focus on the periodic domain. Okay, but such conservation will not be guaranteed anymore if the solution doesn't have enough regularity. So in particular, Onsager conjectured that the threshold Hölder regularity for the conservation is 1/3. So the statement is as follows. If a weak solution is alpha Hölder continuous, and if alpha is greater than 1/3, then the energy conservation always holds. While alpha is less than 1/3, the conservation may fail. Since a few weeks ago, Susan already covered references related to this conjecture, I will just mention highlights ones. For example, the positive part of the Onsager conjecture was eventually proved by Konstantin ENTT in 1994, I think. And as for the negative direction, Camillo and Cyclohidi first introduced the convex integration scheme to the Euler equation, which sort of provides a systematic way of constructing dissipative Euler flows. And with that scheme, the negative part was eventually solved by Iset in 2018, and that proof was refined later by Buckmaster, Camillo, Cyclohidi, and Bicol. Yes. Then what about the borderline case? Well, at the borderline, the question about the conservation holds or not still remains open, but some partial results are available, for example, by Konstantin Cheskidov, Susan, and Shibidukoi, or also by Iset.
Can I ask a question? I mean, there are other spaces one could choose besides these Hölder spaces, and there are various fractional Hilbert spaces and so forth. So, and I know that Buckmaster at one point was working on, I think with Bicol was working on those, but I never saw the preprint. Maybe nothing ever came out of it. I don't know.
So you're talking about.
Can you tell me what happened there?
No, yeah, so they thought they could actually go above the threshold 1/3, but
right.
they would have much less summability, of course.
Yeah.
With much less summability. That's what they were telling me, but nothing came out.
So that's
what is expected at 1/3?
What is expected at 1/3? You can say.
Well, I don't know. I mean, there are some partial results are available, but
Did I
I
show
don't have any
conservation?
bet for.
What does a partial result mean? Either it's conserved or not.
So they prove sort of like conservation in a slightly small, because one can consider finer space than Hölder space.
Okay, different
like
space.
yeah.
Okay,
It
thanks.
might not have a unique answer at the threshold 1/3. Like, you know, if you were maybe like maybe if you are you know, if you are in the closure of C infinity in the Hölder space, which I don't know what's the English word for that. In Italian it would sound like little Hölder. Then I think you can easily prove that it is conserved, the energy. And
What about the, getting back to my original question, what about these Hilbert space structures? What does one expect there?
I don't think there's any conjecture.
Because I think they were conjecturing that they could do it for, which way was it going? They were getting the analog of a Hilbert space alpha structure, right? Some H.
Yeah. So in some H alpha, of course you can.
H alpha.
Of course you could. Okay, so if you have L3, I mean you don't need to be Hölder. If you are in a Bezov space which gives you like L3 summability,
yeah, that's good.
This is still working, right?
Yeah.
The energy conservation.
Yeah.
So
the energy conservation is
exactly. So you could look at the Sobolev embedding, like, you know, taking like higher derivatives and less summability, and look at the Sobolev embedding, and you could try to guess. But I don't know if that is the most sensible thing to do.
Okay.
But so the answer to your question is that there was nothing published.
Yeah.
Not even on the archive,
Yeah, right.
as far as I know.
No, it sounded very interesting, but it was a while ago.
I don't know if they really pushed it too much after, you know, Phil proved the conjecture. So
Yeah, but you see, there was something interesting about the Hilbert space structure. I mean,
Sure.
it was different, and anyhow.
Okay, so going back to the discussion, so in the proof of the negative parts, actually one can prove that there exists infinitely many dissipative Euler flows, and one could ask, are they all physically reasonable? And such question motivates the stronger version of Sager conjecture. So in the stronger version, we require the velocity additionally satisfy so-called local energy equality. So let me first introduce what the local energy inequality is.
So I have one other question. So if you, I know that the alpha bigger than a third does not give you, it gives you conservation of energy, but doesn't give you uniqueness, right?
No, I think uniqueness.
And, or what about vorticity?
So for the uniqueness, as far as I know, it should be like at least Lipschitz. And yeah, then it's about like gradient of U, vorticity, then the corresponding norm is L infinity. Yes.
Okay, so yeah, so you still, so one can't expect to do better than, for uniqueness, better than, unless you have Lipschitz. Is that true?
we certainly don't know either how to make a counterexample.
Yeah, I mean, that would be interesting to have.
Yeah.
Yeah, so about, if we ask about non-uniqueness, yeah, there's like a gap, I mean big gap. Because we could only do up to one circle. Yes, so local energy. So local energy inequality is something like this. So for smooth solution, we have the following identity, and local energy inequality requires the following inequality holds in distribution sets. Equivalently, it can be written as follows: for any t greater than s, and when we consider any local region on the torus, the difference between the kinetic energy at time t and s will not exceed the energy through the energy flux through the boundary. So in some sense, the local energy inequality sort of prevents the creation of kinetic energy in any local region, which exceeds this balance. So there are several benefits of local energy inequality. First, it sort of gives a direction of time. Indeed,
when T is bigger than S, I don't find
yeah. So for any, so this is later time. This is the previous time.
Oh. I see.
Yeah. So it dissipates. So this inequality.
Yeah.
This is just integration of that.
Yes.
Of that one, right?
Yes.
It's probably the other way around, I think.
T is bigger than S.
No, it's correct, sorry. No, it's correct this way. Yeah.
Yeah. So the benefit is it sort of give a direction of time. So like the Euler equation is time reversible. So if one can construct a dissipative Euler flow, then one can also construct the Euler flow whose kinetic energy increases in time, which is won't appear in physical world. But by imposing this local energy inequality, we can rule out such scenario. But more importantly, is it could sort of help it could help to exclude the physically irrelevant Euler flows. Although we haven't had an agreed characterization for the physically reasonable Euler flows, but at least they are required to be recovered as a viscous limit of Navier-Stokes flows. So in this direction, Duchamp and Robert proved the following statement. If weak solution to the Euler equation can be recovered as a vanishing viscous limit of suitable weak solution to the Navier-Stokes equation, so with viscosity nu strongly in L3 topology, then they should satisfy the local energy inequality. So here, a suitable weak solution to the Navier-Stokes equation is, in some sense, one of the most physically relevant solution, in the sense that it allows the singular set only the one-dimensional Hausdorff measure 0, and also one can prove their existence for all time with finite energy. So based on this statement, one can consider the local energy inequality as sort of ruling out condition of the physically irrelevant solution. So now let me state a stronger version of Gonzaga conjecture. So as I mentioned before, for any alpha less than 1/3, there exists an Euler flow. Weak solution to the Euler equation, which is alpha Euler continuous. Which not only satisfies the kinetic energy dissipation, but also satisfies So for this version, there are several results available. First, bounded solutions were constructed by Camillo and Cyclohidi in 2010. And alpha Hölder continuous solutions were constructed with the threshold alpha less than 1/3 by ESET a few years ago. And recently we proved the threshold to 1/7.
Okay, so would you review this again? I didn't quite catch that. My glasses aren't strong enough to quite read what you have there, so you can just say just read what you have, and so I can.
So like
better
we need
sense.
to construct this Euler flow. I mean, this is the conjectured one,
Yes.
like constructing Euler flow which satisfy the kinetic energy dissipation and local energy inequality. So, I mean, so aim is like the threshold 1/3, but so like but bounded solutions were constructed by Camillo and Cyclohidi, and recently the alpha Hölder continuous solutions are constructed, but only up to 1/15. So for any alpha less than 1/15, we prove this. I mean, ESET proved this.
Yeah.
And then we now improve.
No, I'm sorry, I'm still confused because I can't maybe. So what? How is that different from the non-uniqueness and all this? What extra conditions are you requiring here?
This one. So I additionally. So this is the only additional condition. Yeah. Local energy.
Yeah.
So it's more restrictive. Okay.
And how many, you say you can construct a bounded solution for alpha less than 1/7. Is it unique with the bounded property?
So this solution, I think you also proved the non-uniqueness together.
Yeah.
Non-unique, Camillo proved non-uniqueness
Non-unique.
together.
It's not unique.
Not unique.
No. Yeah, I mean, this proof also all contains the non-uniqueness statement.
Right.
Yeah. So, let me add a few remarks. So the constructed Hölder continuous Euler flows actually satisfy the local energy inequality strictly. So these solutions actually have the extra in any local region, they sort of have extra local energy dissipation. But the construction in these two results are pretty different. In particular, the building block flows are different. Okay, so this was the introduction, and now let me move to the proof.
So you have to use really different constructions than the ones that Iset and Camillo and
So
did long
method
time ago.
same, but the building block flows, so like there are different type of building block flows. Instead use just plain waves, we use Mikado Flow, and there are also, I mean, at the beginning you also use Beltrami flows.
Beltrami, yeah.
But I think so far most efficient one is the Mikado Flow. Yeah, but there was some technical difficulty, so I guess ESET just resolved to the plane waves. Yeah. Okay, so before I go into the proof of this stronger version, one may wonder how the proof for the positive part fails when alpha is less than 1/3. So let me briefly mention how the proof looked like. So since we know this smooth solution holds, so the energy conservation holds for any smooth solution. So one naive idea would be we just take the averaging operator to the equation to a smooth solution, and then write the equation for the average solution. Then such equation will contain error, which encapsulates the enemy for the conservation. So for example, as an example of the averaging operator, one can consider some little Pauli projection operator denoted by P lambda, and it only keeps the lambdas free and up to lambdas free and moved. So in other words, one can consider it as sort of cutoff on free SI. So and for the simplicity, let me just denote it by F bar. And now we take this operator to the equation and write it for average solution. And then we'll have some error generated by the nonlinear term. So this error is particularly meaningful when the velocity has much higher frequency than lambda. Then such high frequency term won't appear in the first term, but their self-interaction will have local low frequency terms which will appear in the second term. And that makes the error non-trivial. But so for the conservation, as we did before, we just test the average velocity to the equation. Then we have the following on the left-hand side. And then on the right-hand side, we have the after the integration by parts, we have the following. And since the difference had some nice structure, after some computation, one can estimate it by the following. So if alpha is greater than 1/3, such error will converge to 0 as the lambda goes to infinity, and that implies the energy conservation. On the other hand, to prevent such error from vanishing, one can consider some ansatz which contains the high frequency from the end of spectrum. So with such ansatz in mind, now let's move to the proof for the stronger version. So the proof is based on the convex integration scheme, which is a nonlinear iteration method. So at each iteration, we're gonna construct an approximate solution which almost solves the Euler equation and almost satisfies the local energy inequality. So in other words, they solve the relaxed system, allowing some error. So this is the stress tensor, Reynolds stress error, and IQ is unsolved current error. And the relaxed system will look like this. So it allows divergent form of error. The equation. And in the inequality, it allows the following type of error. Here, we further require the Reynolds stress to be symmetric, and kappa q is determined as 1/2 of the trace of the Reynolds trace. And since we want the limit solution to satisfy the original equation, all error should converge to 0. In fact, there is enough to be in L1 space, but in the proof we can actually obtain in C0 space. Okay, then one may wonder what's the motivation of this relaxed system. So to see this, let's recall the answers that we have in mind. So we consider the answers which contains the high frequency at the end of spectra, and one possible form would be like some solution which consists of perturbation whose frequency is localized to lambda q, and it decreases as the index goes to infinity. So on Fourier side, the picture will be look like this. So the solution will be supported in the spherical shells, whose radius is like highly increasing, and actually the radius is like lambda q plus 1, and so on. And the natural approximation for such solution would be like considering up to q shells. So then the equation for this approximate solution would be the equation for the average solution. And if you see the equation for that, it has the divergence form of error, and one can also observe the inside tensor is always symmetric. So that sort of motivates the Reynolds stress error. And in a similar way, one can also write the local energy inequality for the average solution. Then one can see the following form of errors. In particular, this unsolved current error is generated by the cubic term, non-linear cubic terms. So then our task would be, so to construct such approximation, our task would be as follows. For a given Q-step solution, we aim to find a perturbation from the previous solution which generates the next step solution, which satisfies the following conditions. So it should be fast oscillatory and divergence free, and more importantly, we want them to cancel out the all previous errors. In this way, one can upgrade the previous error to a much smaller one. So let me first, let's just focus on the first equation first, and write the equation for the perturbation. So here I use the Q-step equation, and from there we obtain the previous Reynolds stress error. And also from this equation, one can observe that since the frequency of the Q-step solution is localized to of order lambda Q, so is the frequency of the Reynolds stress. So on the frequency side, it will be of order lambda Q. On the other hand, if the lambda Q grows very fast, for example, double exponentially, all linear terms will have a frequency essentially localized to lambda Q plus 1. So as we usually do in Fourier analysis, one can split this equation into two parts, the low frequency mode and high frequency mode. So in particular, in a low frequency mode, the equation will look like this. So here, for simplicity, I just denote the low frequency part of pressure, the perturbation of pressure as some function C. And we have the previous Reynolds stress. So our aim is now reduced to find perturbation, which is highly oscillatory, divergence free, and which solves this equation. To this end, let me recall some geometric lemma. One can find, for example, such lemma in Camillo and Zakulihides' paper in 2003. So the statement is as follows. If we have some set of vectors in the integer lattice, which satisfies the following property, so their tensor product with itself forms a basis of the collection of all symmetric matrices, and their summation is equal to identity. So actually the cardinality would be 6. Then for any symmetric matrix which is in a small neighborhood of the identity, we'll have the following representation. So here the coefficient AF is a smooth function in the matrix argument. Well, first, finding such vector is simple. One can just, as an example, one can just consider the following set. And then, since for identity, it already have a representation, it can be written as a finite summation of rank 1 tensors. One can just consider this matrix K as a sort of perturbation that one can find some smooth coefficient. So once we have this lemma, we can write the matrix on the right hand side as the finite summation of rank 1 matrices, and then the natural choice of the perturbation will look like this. So here I just choose this function C as a constant, some sort of a constant. So we have and to make the perturbation highly oscillatory, I first add the plane waves whose frequency is lambda cube plus 1. And I choose some vector which is orthogonal to f. So in this way, this flow is divergence free, so that we can make this perturbation almost divergence free. I mean, later we can always add a small correction. However, if you consider the tensor products of this perturbation with itself, it generates not only self-interaction term, it also generates the interaction between different plane waves. And that sort of make a trouble. So there are several ways to deal with this problem, but among them, the most efficient way is using so-called Mikado flow. So now let me introduce some Mikado. So this flow was first introduced by Daneri and Cyclopidi in 2017. And these flows became one of the main ingredients in the full proof of Onsager's conjecture. So consider.
They're not due to Mikado.
Sorry?
They're not due to Mikado. How does Mikado's name enter here then?
Because, well, they are pipes, they are long pipes,
Yeah.
long pipe flows.
Yeah.
And Mikado is this game that you play with the, long sticks. Have you ever played that?
I don't think so.
Yeah, so it's this game that you get these bunch of sticks, you let them go on the table, and you have to get the sticks out without
That's where
the other ones. You probably played that, right?
No, I don't. I guess I've heard of it, but I don't know.
Yeah.
So that's where it comes from.
Yeah, that's where it comes from. Yes, and I think it's a Hungarian game. And Laszlo is Hungarian, and I think he picked it up.
I know the game, but I didn't know that the name is Mikado.
Yeah. So I looked it up on the internet because I thought it was some Japanese.
I also thought.
It's actually Hungarian.
Okay.
So Camilo just gives a nice motivation of these flows.
Yeah.
But you can ask directly Laszlo next year when he comes over.
All right.
Okay.
More behind stories. So let's say some vector in integer lattice is given, and also some point on a torus is given. Then one can easily draw some line with starting point and the direction vector. And then take its periodization. And one can easily find the associated function, which is smooth, and it is independent of the variable along the line. And furthermore, it is supported in a small neighborhood of these lines. So the picture of the support will look like this. And one can easily see that it satisfies a divergence-free condition because the associated function doesn't change its value in the direction of f. And by the same reason, it solves the stationary Euler equation with zero direction. So the solution of the flow of the flow which solves the stationary Euler equation is called Mikado flow.
No, I still haven't understood the flow though. So what do you do here? You just say it again.
So
Too fast for me.
So when first there is a vector f in the integer lattice.
You have to find this or
Just any
okay.
is fine.
Yes, and then what?
And then consider some arbitrary point.
Yeah.
This can be also chosen whatever you want.
Okay.
And then you draw a line and maybe periodization on torus.
So the line just keeps on going though, right?
Yes, yes,
Okay.
yes.
So that's just the start of it. It keeps on wrapping around.
Yes, yes.
But F was chosen to be in Z3, so the line is a.
Yeah, so
Yeah, so it will end at some
Eventually
point.
comes back to itself.
Yes.
Yeah.
Yes,
And
at
it's,
some point, yeah.
and it's very important it comes back to itself.
Yes,
Okay.
otherwise.
I mean, it's not invading because you will use many of them, so you don't want them to actually overlap.
Okay. Okay.
Yes.
Yeah. Yes. And then.
And you choose the associated function which is supported in the small neighborhood of these lines. So this function is supported here.
Okay.
But this function is independent of the variable
Along that direction.
so that it satisfies both divergence-free condition.
Okay.
And
Okay. Now, where does this game come in?
I mean, you mean Mikado game
Yeah.
or like? Well, I guess these pipes corresponds to the sticks.
Oh yeah. I mean, if you don't see it on the periodic torus, right? If you see it in R3, you just see a huge line, right?
Yes.
So you just see like this very long stick, if you want.
Okay.
Why does it satisfy those equations?
So this you choose this associated function.
This function lives in a neighborhood of the periodic orbit, right?
Yes, and also at the same time, it does change its value in this
Along the
direction.
Along this direction.
You can always choose such function. Yeah,
Okay.
so it satisfies divergence-free condition, and I mean, this can be written as follows. So it again is 0.
Good.
Yeah. Yes, and if we further assume the mean of this associated function is equal to 0, then the rescaled Mikado function would be frequency essentially localized to lambda cube. So this could be a good substitute of these plane waves. But the benefit is they have a nice picture of support. So now let me revise our perturbation by using Mikado Flow. And of course, for each f, I'm gonna choose a suitable starting point so that all Mikado Flow have a disjoint supports. In this way, when you take the tensor product with itself, only self-interaction term will survive. So, and then now if you take the low frequency part, which is same with taking mean here, then we obtain the desired form, so which cancel out the previous errors. I think. I didn't wrote it, but yeah, it matches with the previous error as long as this is equal to 1. But since this is staying with the mean of the square without lambda, so one can have this simple restriction to the associated function. Okay, so this perturbation is the desired one, which is highly oscillatory and cancel out the previous Reynolds stress. And now we should also consider the local energy inequality together. So there, where's the where to cancel out the previous unsolved current error, we're gonna use low frequency part of the cubic term. So now our aim is to find a perturbation which solves these two equations. And also the equation what we just solved. Now the problem looks much complicated, but in fact we can make these two equations sort of decoupled. So what we did is as follows. First, consider some vector value version of the geometric lemma, and one can write this previous unsolved current error as the following form. So again, this coefficients is smoothly depends on the error, and it can be written as follows: that a natural choice of perturbation, which solves the first equation, would be the following. But of course, all these Mikado flow again have disjoint support. Okay, and now if you turn to the second equation, when you take the tensor product with itself, there will be the self-interaction term appear. But we move all such terms to the right-hand side and consider them as an error, and solve as before. Solve this equation as before. Then we're gonna add a new set of vectors. So this vector comes from the original geometric lemma, and we'll have some suitable coefficients and associated Mikado flows. So here, since the low frequency, when you consider its low frequency parts, you will see the mean of cubic. So we need the following condition. So this is similar to what we required here. And this one, as before, we require this square, mean of square satisfies 1. But if we further require their cubic, the mean of their cubic is equal to 0, this term won't appear in the low frequency part of the cubic term. So this perturbation still solves the first equation, so that that one is our desired one, which cancel out the all previous errors. Okay. So now, so this is our base form of ansatz. So for the simplicity, let me just write it as follows for the remaining term. And now let's move to the higher frequency modes of the relaxed equation. Then, since the size of the errors are related to the size of perturbation, and that eventually affects the regularity of the solution, so our aim there is to minimize the solution as much as possible. And among all the errors, the worst error comes from the transport term. So let me talk about transport error. Which looks like this. So So in the paper of Master Camillo, Iset, and Zachlidi in 2015, to minimize this error, they affect the base flow by the previous velocity. So idea behind this as follows. The material derivative, meaning that the time derivative together with direction derivative, describes the change of the quantity along the flow. So if we move the base flow, if we transport the base flow so that it doesn't change its value along the flow, then their material derivative will always zero. So, using that idea, we first introduce the backward flow map, which solves the following PDE. And then the transported Mikado flow would be described as the composition of rescaled Mikado with the backward flow map. But to keep being divergence free, we need a small correction. Okay, but these refined ansatz can't be proceed for a long time, because otherwise this flow map will destroy the frequency localization. So to resolve this issue, we just divide our time interval into smaller one, and at the beginning of each time interval, we just restart the Mikado flows. So the picture would be as follows. So let's say the size of time slot as tau. So there would be tau and 2 tau, 3 tau, and so on. And at the beginning of each time slot, and this is the torus, we assign the Mikado flow and then let them flow. And we just glue them together by using partition of unity. So in this way, as long as the size of perturbation is small enough to satisfy the following property, the frequency localization still holds. But this generates another issue, which is there will be an interference error between the Mikado flow between Mikado flows from different time slots. So to deal with this interference error, we made the following observation. The support of Mikado flows, the transport Mikado flows, in a small region for a short time remains almost in Q. So in other words, as long as we restrict this to the region, the original picture of the thin cubes will still remains. The original picture will still remains up to some little perturbation. So to do this idea, we then divide the torus into smaller cubes and assign Mikado flows to have a disjoint supports in conjective cubes. And then to avoid the interaction between Mikado flows from different time slots, we allow the suitable shifts to each cube so that it doesn't interact with the Mikado flows from previous time slot. Yeah. So in this way, we can avoid the all interference errors, and that eventually improve the transport data. However, this spatial discretization generate another error, and that explains our Hölder regularity 1/7, which is less than the conjectured one. I think I should stop.
Thank you. Questions?
Well, you said it at the very end, but this 1/7 comes from this
Spatial,
this spatial
discretization. Yes. Yeah. So actually, in the full proof of Onsager conjecture, I mean, they also met a similar issue, but what they did is sort of gluing argument, meaning that for given the previous solution, they sort of upgrade this Reynolds stress by solving the equation exactly. And then if they glue them together, they can make the new Reynolds stress error almost have disjoint support in time interval, and then they could avoid such issue. But we couldn't apply such technique to here, but because of some technical issue, so yeah, we just use the following.
Each time you cut off and you make these partitions, you're going to pay something.
Oh, sure.
Somehow.
Yeah, I can imagine.
That's the idea. And so the more you want to gain, the less you should actually try to cut off. Other questions?
Well, thank you very much for a nice talk.
Susan, do you want a question? Do you have a question?
Basically, at the point at the end, why is ensuring the local energy inequality is satisfied making life difficult for you in terms of this time breaking up that it follows, again, along the lines of earlier proofs which did not address the issue of the local energy inequality. Where does the difficulty come in?
So, well, for me, it was more like technical difficulty, but for example, there's sort of like cutoff in times, and then that will generate sort of energy, I mean, creation, because if you imagine the time cutoff, there will be an increase, I mean, the increase of energy and decrease of energy and so on.
Mm-hmm.
So
okay, thank you.
That sort of, yeah, violated the local energy.
Other questions? Okay, if not, thank you very much.